Hello everyone, you are warmly welcome to this webinar of ElFys. My name is Mikko Juntunen, I'm the founder and CEO of ElFys, and together with me here is Juha Heinonen, one of the co-founders. We will be telling you about the company first of all, then about black silicon photodiodes, technology, advantage and use cases. If you have questions, you can place them in the chat on the top right corner of your display during the presentations, and afterwards then we can answer at least some of those. So the agenda, the introduction to black silicon photodiodes. I'll tell briefly what they are. There will be some technical benefits and innovations described, use cases and applications, and then Juha will continue with an overview of the quadrant detector development project and applications of that. What ElFys is a company providing photodiodes with sensitivity exceeding anything seen before. It is based on patented nanotechnology, which we have already proven in various applications to work and provide the benefits that we say they are. And as we speak, we are preparing and building high-volume manufacturing with industrial partners. So, light detectors with superior sensitivity by using advanced nanotechnology and atomic layer deposition techniques. We founded the company in 2017, so it's almost seven years ago, with a team of scientists from Aalto University, which we have then complemented with expertise on industrial manufacturing, sales and marketing, etc., and have presently a 15-member team with excellent profile of expertise. And out of those, 7 have doctoral degrees, 6 are females. We are representing 5 nationalities and speaking 7 native languages, plus English, which is a foreign language for all of us. We have served more than 70 customers in 17 countries, and our cumulative sales is, well, about 1.7 million euros, so we are still in the early growth stage. We capture every ray of light and wide band. In silicon, it's 200 to 1000 nanometers, and we also provide a very wide acceptance angle, meaning light coming from high angles to the surface. With this technology, we can provide better signal-noise ratio, which can be used to improve whatever you are measuring, or you can use less light for whatever you are measuring and save energy, extending the battery life. Or you could use the same by making the diode smaller. We also customize, so we can make your design. This is how it looks like, or actually it doesn't look like this because it looks totally black. This is an electron microscopy image of it, and as you can see, the structure is on the same scale, same order of magnitude as the wavelength of visible light, which is about 400 to 700 nanometers. I dropped a few coronaviruses there just for scale. So that structure absorbs all the light. But that's not enough. We also need to collect the charges generated by the photons absorbed, and that we accomplish by atomic layer deposited dielectric layer on top of this structure. So, black silicon induced junction photodiode. Here are some performance data. This is a direct comparison to some competing photodiode, other state-of-the-art technology. The purple curve at the bottom is that. The orange-yellowish curve is ours when encapsulated in epoxy packaging, and then the top curve is ours from air to silicon. And as can be seen with the very commonly used green light in wearable health monitoring devices for pulse measurement, our signal level is 1.5 times higher. And since we are not sacrificing in noise, this means that the performance can be improved a lot. Photodetectors are used in wide range of applications nowadays in products like wearable health monitoring devices, cameras, barcode scanners, in your cash registers, fiber optic links, blood particle analyzers, etc., etc. We have selected market segments with a huge addressable market that are analytical instrumentation, defense sensors, wearable health monitoring, and image sensors. As an example application on the analytical instrumentation is spectroscopy. With higher sensitivity, you get higher signal. meaning that in a spectroscopy you get higher and narrower peaks, meaning that you can detect lower concentrations of material or separate close to each other materials better from each other. Another application example, wearable health monitoring devices like smartwatches or rings that are measuring pulse, heart rate variation, blood oxygenation, etc., using light, illuminating skin and measuring what comes back. With our technology, this can be improved, either improving the signal to be collected to extract something better out of it, more precisely, or equivalently use less light to save energy and extend the battery life, or facilitate an even smaller device by using an even smaller photodiode to do what is enough. Or in image sensors, we have proven that we can turn an image sensor black, meaning that we can improve the quantum efficiency of image sensors, providing essentially what is shown in this trivial image pair here, that especially in low light conditions we can facilitate our customers to acquire reasonable images. And now I move on and give the stage to Juha to introduce the 4-quadrant detector development.
Hey, so I'll be talking about what we have been developing, and mainly I'm focusing on this quadrant type of detector development project that we have ongoing at the moment. So first of all, what I mean with a quadrant detector is here. So on the right, you can see that this means that we have the active area is divided into 4 quarters that can each be read separately. And if you then have a laser spot that is hitting somewhere within this area, you can then, by looking at the signals from each pixel, you can then determine the location of the spot very accurately. And you can imagine that this kind of detector can then be used in all sorts of applications where you need to do some precise aiming or alignment or something like that. So some examples could be like optical laser communication, either here on Earth or in space, or autocollimator, or one popular one is also this kind of a laser guidance system, which usually is using this YAG laser that is operating at 1064 nanometers. And also in our product development, we took this 1064 nanometer as the baseline, so we have been doing all the optimization that wavelength in mind. So at that wavelength, we are talking about near infrared. And that is a rather challenging wavelength to detect with silicon. And the reason is that the absorption depth starts to become rather long, meaning that you are losing some of your signal because it is going through the entire detector. Of course, obvious solution is to increase your thickness of your silicon substrate. But then, unfortunately, that also makes the detectors slower, among other things. So, in reality, you have to do some kind of a compromise between the rise time and the responsivity of the detector. However, with black silicon, we can get a significant improvement at this wavelength also. And here on the right, you can see how our responsivity, which is the blue curve there, compares to some other quadrant detectors that are on the market at the moment. And you can see that at the YAG laser wavelength, we can see significant improvement in the responsivity using our black silicon technology. So that's why we started to look into this product segment and this wavelength, because we can see this big improvement possibility here at this wavelength. So why is then this black silicon so much better? Of course, one big factor is that there is practically no reflection, so that already helps a lot, but that is not the only thing that explains why the responsivity is so much higher. Another thing that is going on is that when the light hits the surface, it doesn't just go through in the same angle, but instead this black silicon structure, it scatters the light, meaning that the light will travel a longer path inside the silicon, and that way we can absorb a larger amount of the photons within the same thickness, and that way increase further the responsivity. And on the right hand side you can see a picture from one of our from one of our publications where we have studied this phenomena. So if you're interested, you can find more details from this paper that is listed there below the picture. So since there is a clear improvement achievable, let me now introduce you the new product we have been developing on this quadrant market segment. And the structure is here, what we are going to build or are building at the moment. So first of all, there in the center you can see the actual photodetector chip. It will have a 14 millimeter diameter. It will be then packaged on a TO can, which is in diameter roughly 1 inch or about 27 millimeters. And we are planning to have two different versions. One which just has the detector and nothing else. That will have then 7 pins in the TO can. And then another version that will have this kind of a heater integrated below the chip, and also a temperature sensor, and that will then have 11 pins in the TO can. In addition, we also have a window on top of the detector, and that window will also be coated with an anti-reflective coating on both sides that is optimized for these 1064 nanometers, so that we don't get any optical losses from the window itself. So what kind of performance can you then expect from this product? Here is some preliminary data. As said, this development is still ongoing, so this data is not final, and some parameters are still missing and coming in the near future. The responsivity that you can expect at this 1064 nanometers at room temperature is around 0.64 amperes per watt. Operation voltage will be 140 volts, and at that bias voltage you can expect to have a 16 picofarad capacitance and around 15 nanosecond rise time. And since we have also this heater integrated, that allows you to heat up the detector, and that way you can even further boost this responsivity at this 1064 nanometer wavelength. And here is some preliminary data on the right, how the responsivity increases as a function of temperature. So you can go even up to something like 0.77 amperes per watt if you heat it up enough. And yeah, some samples we have obviously already, since we have the data here, but there is still some work to be done. So we are estimating that we will have the first samples ready to be delivered for customers by the end of this year. And yeah, then what can you benefit with this higher responsivity that you can achieve with our black silicon technology? One example is here in missile guidance. And the idea here is that the operator here is pointing with a laser pointer to target, and then you have a detector in the missile that then locks on to the target based on the reflected laser beam from the targeting machine. And what is important here is, of course, from how long you can lock on to this target. And we have done some calculations that with this higher responsivity, you could increase the distance by up to even 30% in some conditions, how long the lock-on can happen on the missile. Another important thing is this safe zone where you can launch this missile, and this higher responsivity should also allow you to increase the safe area where you can launch the missile. That was what I had about the Quadrant product, but that's not the only development project we have ongoing at the moment. So here's a quick little teaser what else is coming in the future. So as mentioned, the silicon is not optimal material for the infrared light detection. So that's why we are planning to go beyond the limitations of silicon by utilizing a different material. And in this case, it would be germanium. And where the development is at the moment is that we have managed to reproduce this same kind of nanostructuring process on germanium to make it completely black. And here on the right-hand side, you can see the absorption of the black germanium compared to the silicon, which is the black curve, and germanium is then the blue curve. And you can see that in both cases, the absorption is almost 100%, so basically no reflections. But compared to silicon, this germanium, then the absorbance stays high, much higher in the wavelength range. So you can extend the responsivity even up to over 1.7 micrometers compared to this 1.1 micrometer that you can achieve with silicon. So we have this process to make it black, and then the next step what we are working on at the moment is to then apply it and make a photodiode out of it. So we have this, or we are part of this Business Finland project called PhotonWare at the moment, where we are then where our goal is to implement this kind of a black germanium photodiode. So that will be coming up hopefully soon in the future. And with that, I think that was everything I had to share at this time. Here you can find some contact information if you want to contact us, or Mikko especially. And I think then next it would be time to take questions from the audience. If you, Mikko, also join me.
Sure. Thank you very much, Juha. No wonder that he was awarded the Best Dissertation Award in Finland the other year. Excellent presentation. I hope it made all clear. And I see that there are a few questions in the chat box. The text is a bit smallish, so I need to squeeze my eyes to see them. Okay, the operator made them bigger. The first question there is, I'm reading them for clarity. What is your production setup capability? And of course, an excellent question. We are presently manufacturing ourselves here in Espoo area using the facilities of Technical Research Center of Finland. Manufacturing meaning that we are processing the photodiodes out of silicon wafers. The packaging of these components is done with external partners in various parts of the world, depending on what is being built. But we are, as we speak, building industrial manufacturing cooperation with external foundries in France and in Malaysia, so that we will be able to provide these in high volume in a reasonable future. I'll jump to the question of Victor because it was kind of answered by Juha just a few moments ago. We are not in 2 to 6 micrometer region. We are just targeting the region between 1 and 2 micrometers as we speak. The question of Emma about what are the best use cases where black silicon characteristics are most beneficial. Obviously, this is something that we have been looking at through the short history of the company, trying to find the sweet spots on where the performance improvement is most relevant and reasonable. And also there has to be a business match. And the target areas that we are now working with are excellent examples. And kind of unfortunately though, the example given by Juha about this missile guidance is at the sweet spot. Maybe I'll throw to Juha this question of John Stevens about the responsivity of quadrant detectors.
Yeah, so responsivity at other wavelengths than 1064 nanometers. So if we go back to my slides, a few slides back.
That's the first
It's going. This one. So here actually the blue curve is measured from on actual quadrant chip. Of course, it's just a bare chip in this case. So in the final component, we have, of course, the window. So that will affect somewhat the responsivity. So it's optimized for this 1064 nanometers. So there you can expect to have very little difference compared to this responsivity. But then it will have some effect on the other wavelengths. But certainly it can also detect other wavelengths, and the responsivity will be something, but not as high as in this picture. Of course, there is a possibility that we make a version with a different kind of window, so then we can also tune it to a bit different wavelength range, but that's at the moment how it's going to be.
Great, thank you. All right.
Next one.
Which type of a chip you're using in? It's not fully clear what does that mean, so maybe we'll move on to spectroscopy-related question. Or Alexei is asking, you mentioned spectroscopy and cameras applications. It typically assumes megapixel size arrays. If I got correctly, your current products are single area diodes. Any comments on that? And of course, an excellent question, and that's correct. Our products are single area diodes and also multiple area diodes, arrays and matrices that we can be doing on custom basis, but not megapixel devices. Our approach to this megapixel is that with our technology, a CMOS sensor having the megapixels on one side can be changed to black on the other side. And we are not assuming that we would be starting doing these megapixel arrays, but we can serve the companies manufacturing them by providing the technology of improving the quantum efficiency there on their facility. I hope this answered the question.
So next up is, what are the drawbacks or downsides of black silicon compared to conventional detectors? Do you have some ready answer already?
Well, you remember we started with wondering how can we handle those, because this black structure is sensitive to touching, and we realized that rather early that, well, by breaking them, that it is somewhat difficult. But we ran a project on developing the methods of handling them safely, and we can package them and also provide our partners means of handling them safely. So that's one. Do you have some other?
Well, of course, it can be a plus side or a downside, but we are seeing everything. So if you want to see only some wavelengths, then you might also see the others. So you might need some kind of a filter to limit the wavelengths that you are seeing. But on the other hand, it can be also a big plus that you can see with the same detector many different wavelengths.
Right. Yeah, maybe actually the question of Jenia about the rise time. There are some differences with our technology, so maybe you'd elaborate on that a bit.
Yes, of course the rise time depends on the size and the type and everything, but with the quadrant I showed you, we are getting this 15 nanoseconds, which is actually rather fast for this big size of detector. So we have managed to do some improvements in the process to get it faster, so maybe not all of the old products are as fast as this one. So there are some tricks that we have been doing in this case to speed up the responsivity of the detector.
Right. All right. Then there is a question related to the chip. This probably relates to an earlier question that's not visible anymore in the chat for us. For quad detector.
Which type of chip you're using in quadrant, I think.
And that's the one that you introduced a moment ago. Maybe explain a bit further if possible. Yes. Without disclosing anything sensitive, obviously.
Of course. It will be a silicon chip, as mentioned, so it's black silicon. And the wafer type will be N-type. And you saw the rough dimensions, so it will be the active area will be 14 millimeters in diameter, and the whole device would be then like roughly 1 inch. So yeah, and it will be like a pin diode, so not like an avalanche or anything like that, so normal PN junction diode.
So 4 separate diodes in single chip.
Yes.
Right. So then there is one Jianhui, I hope the pronunciation was even at least close to correct, thanking us for a great job. Thank you. Any cost guidance of the black silicon technology? Is it on 8-inch or other size of substrate? And on the costs, I'm not giving pricing here, but of course, initially when we start doing something new, there are some costs related, and I can say that they are not the cheapest on the market. However, the black and ALD technologies that we are using are not something extremely fancy and expensive. They are widely used in other areas of semiconductor business. We are just applying them in a new way. We are making here in 6-inch, and also the European facility is 6-inch, but the other one that we are having in Asia is going to be 8-inch. Anything you want to add? Probably not.
Yeah. That's at least all the questions so far in the chat. There's still a few seconds, maybe time to write more, but if not more,
very happy to see so many questions, and this sort of became a live discussion that we desired.
Yes. And well, this was of course our very first webinar ever, so all sorts of feedback or comments are of course very much welcome if you have any, so we can then improve next time. And I think we had some kind of a plan that we do maybe twice a year, something like this, so you can expect to have a second session sometime in the future.
Yeah. All right. Thank you very much, and thank you for your kind words in the chat, and see you next time. Bye bye.